I want to go back and talk a little bit about singlet and the triplet and the energy gap, because this is something that some of you maybe is new and maybe not following very closely. So what happens is, when you think of a molecule, the way the energies are calculated, so you have the ground state, and then you have excited state. So if you have two electrons in the pi orbital, so if you take a molecule, you will have a pi orbital and a pi star orbital. In the ground state, the two electrons will be here. So when you shine light on this molecule, one of the electrons will go from here to here. So we will be calling that as pi and pi star. This is pi, this is pi star. So in the ground state, both the electrons are in the pi orbital. In the excited state, there is one electron in the pi and the other one is in the pi star. Okay, this is there are two electrons, one in the pi, another one in the pi star, but they have opposite spin. So when you say pi, it is this. When you say pi star, it is basically this. This is the pi and this is pi star. But they are in the exactly same area, excepting that in this case the two electrons are overlapping. In this case, they are staying separate. So they are in the same space. Okay. Now what happens is, if to calculate the energy of the singlet state, what we will do is, we will take some atom with respect to this. These two electrons are attracted to this. So based on the attraction, we give the energy of this number, let's say 100 kilocalories. Okay. This one is completely based on attraction between the two electrons to the nuclei. Now, if these two electrons, they also will be repelling each other. If they repel, means when they attract, the energy goes down. When they repel, energy will go up. So the number that you calculate here is not completely correct, because you will have to worry about the repulsion. Okay. How much is the repulsion? It depends upon where the two electrons are. If they are closer, repulsion will be large. If this far apart, the repulsion will be less. So whether they are going to be closer or farther, it depends also on the orbitals, and also depends upon the spin. If the two electrons, that is one electron is here, another electron is over here, the repulsion between these two depends upon the spin, because the spin will control where the two electrons are, whether they are going to stay closer, whether they are going to stay apart. Okay. So what is going to happen is, now when we calculate the energy, the original number was 100. Now you worry about the repulsion, you put another 20 kilocalories, and then if the two, because of the spin, the two electrons have the opposite spin, they will stay closer to each other. They will not go too far away. If they don't go too far away, what we guess is lesser than what is the reality. So we have to know exactly where the electrons are. It is not possible to know where the electrons are, so we guess. So if the electrons are between these, so this is the area, and this area, the electrons are going to be somewhere here. But if it is here and here, the repulsion is going to be lesser compared to if the electrons are over here. These two are closer. So whether when we guess, we just put it on number 20, But if they spend more time over here, that means the repulsion that we guess is lesser than what the reality is. So really the 2 electrons are staying here, that means this number should go some more up. So the energy of this state is going to be 130. So for example, you take here. So S0, S1 without the repulsion, and you add up all these numbers, it goes over here. So the real state is this one. Okay. So this is for the singlet. If these 2 electrons have the same spin, now what is going to happen is the triplet state is going to be 100 plus 20, and now if the 2 electrons they don't stay here, then that means it is going to be less repulsion because they are not closer to each other. So what we guess is more than what really is. With the 2 electrons we assume it is spread over here and spread over here. But if the 2 electrons have the same spin, one stays here, one stays here. So what happens is the number that we guess is higher than what is there in reality. So the number is going to go down. So instead of plus 10, it will become minus 10. So this will be 130, this will be 110. So that's what happens between singlet, and this will be triplet. So whether it is how much is the separation depends upon the overlap. If the 2 orbitals are overlapping very well, that means there is a good possibility the 2 electrons can be closer to each other. If the 2 orbitals are perpendicular, they don't overlap, that means the electrons will stay apart. So the repulsion will be less. If it is less, that means the gap will be small. Okay? That is the basis of the singlet triplet gap. Now the question is, why are you worried about singlet and the triplet? Because the triplet and the singlet, since they have different spin configurations, the transitions are some of them are allowed, some of them are forbidden, and then in terms of the chemistry, singlet and the triplet, they will do different things. If you know, you might, I think some of you record the emission spectrum. Singlet emits, it is called fluorescence. When the triplet emits, it is called phosphorescence. They come at different places, they don't come at the same place, and they also have different lifetimes. Singlets will have, fluorescence will have like nanoseconds, and the phosphorescence will have a few microseconds, milliseconds or seconds. So that's why singlet and the triplet you have to know, because that is what half of the photochemistry is about, singlets and the triplets. Okay. Now you have any questions on the singlet, triplet? Clear? You are asking some questions. No questions. Okay, so I was talking about remember, this is what we talked about, right? So basically we wanted to know something about the molecule. Something about the molecule is all contained in this file function which is called the psi. That psi, it represents the positions of electrons, position of the nuclei, and the spin of the electrons, all three. But we also realized even to figure out the positions of electrons is not that easy. So if all three are changing, it is not going to be easy to figure out where the electrons are. So we made an assumption, Born-Oppenheimer Approximation, in which we assume the positions of nuclei are fixed. For that fixed configuration positions, we calculate all these things. But in reality, it is not fixed. In reality, the two atoms are always moving around a little bit. If it moves around a little bit, the electrons are also moving around a little bit. If the electrons are moving around a little bit, all the things that we got here is not completely right. But there is no other alternative. So we will proceed with the same thing. Okay? So motions of electrons in orbitals are much more rapid than nuclear vibrational motions. So if you have a nuclei A and B, the distance is, let us say, 2 angstroms. So the electrons are somewhere here. If this electron, if the nuclei moves a little bit, it will become 2.5. Now the electrons will quickly adjust to these new positions. How fast it adjusts? Because it's much, much faster than how fast the nuclei can move. So the electrons are like a small bee, whereas the nuclei is like an elephant. For the elephant to move and for this beast, the bird to move, they are very different time scales. So when the bird is moving, the elephant is still trying to walk slowly. Okay, so here. So now, assuming this is true, what we'll do is we will fix the nuclei positions and calculate this. But now we know for certain the nuclei is not fixed, it is moving. So now we have to face the reality and come back and try to understand this molecule. Okay. Have you vibrational spectroscopy where harmonic oscillator and all this stuff? Do you know a little bit? So here, so what happens is, in a molecule, all the things that we talked about here, it takes assuming this position here. The position is the molecule is stationary at this point. When it is at this point, when it is stationary, the electronic configurations are these, energies of all this stuff are here. But then this is the 2 atoms. But these 2 atoms, they are always moving around, vibrating. When they are vibrating, the distance between these 2 is going to be here or here or here and here. So they vibrate between these 2 places. They just move back and forth like this. When they move back and forth like that, the electronic configurations will slightly change, the energy will slightly change, but not much, but it will change a little bit. So when we are talking about 100 kilocalories, if it changes by 1 kilocalorie, it is not a big number. Okay? But you have to realize it is going to change. So yes, this is what is called as, if you have 2 balls connected by a spring, if you hold one ball and pull it, this one will go back and forth. So in a molecule, what happens is A and B are held by a bond, that is two electrons are holding these 2, that is like a spring. So because of that, these 2 just always move like this. It is so that one is called as harmonic oscillator. That is, it is just it is a symmetrical oscillation. But what happens is this will never break. So when these atoms are vibrating like this, the bond will not break because it is still the 2 electrons. If it goes far away, it will pull it back. If it comes too close, it will push it away because the electron repulsion will be large, so it will push it away. So it will go closer, farther away, come closer. That's what will happen. Molecule will always be doing this stuff. When you have a molecule in the beaker, it is always vibrating. Okay? Now we have to understand what this means. Okay? So this is the position, this point is the one that we assume fixed and do all this stuff. But now no molecules is stationary. All molecules are vibrating at all times, independent of the temperature. So this is the molecule is going to be vibrating between this place and that place. This represents the distance between these 2. This may be 3.5. This may be 3.7. And then if you give a little bit more energy, so when the molecule is A and B are together, they just go on like this. If you put a little bit, another 5 kilocalories more, it will go a little bit more like this. Another 10 more kilocalories, it will go like this. So the energy will keep on increasing. That's how the chemical reactions take place. So this represents, these lines, they represent the vibrational levels. But if you notice, the energy of this is smaller than this one, this one, this one, this one, this one. But it is not that much difference, but it will be like 100 kilocalories, 101 kilocalories, 102 kilocalories, and like that. So the energy will increase slowly. But if you keep on increasing, eventually it will break. Okay? So these are called as vibrational levels in a molecule. So this is like the atomic orbitals or the orbitals, which describes the positions of electrons. The vibrational levels describes the positions of nuclei. So if you have a carbon and a hydrogen bond, where the carbon and the hydrogen in the nuclei, it is defined by the distance. If it is 2.5, 2.8, 3.2, 3.7 like that, it will keep going. Okay? But so depending upon these positions, so as you see here, if you notice, this is the distance of 2.5. If you give another 5 kilocalories or something, it will vibrate between 3.7 and 2.8. Put some more energy, it will go to 3.9, and then it will go to much shorter distance. Okay, so this is the vibration 0, 1, 2, 3 like that. So when we talk of a molecule, simple molecule, we assume it is the vibration level 0. Even at the 0, it is vibrating. Okay, but if we keep, that is what we do when we do the reaction in the lab. We heat the compound. As you heat it, it will start vibrating at a longer distance. So this is true. But then, when you talk about, for example, the molecule, the two atoms are distance of this or that. So when you say vibrational, the molecule is between here and here. It can be having a 2.3, 2.5, 2.9 or 3. So it can have a distance of any one of these things in the line, 2.5 or 3 or 2.3 like that, any one. So it may be like this, may like this or like that. Which is the most possible at that particular vibrational level is given here. So if you have a molecule vibrational level 0, most of the time it will be somewhere here. See this probability distribution, it tells you the atoms is likely to be here in this vibration level 0. If you put little bit more energy, it will go to vibration level 1. Then the probability is going to be more is here and here, and put more energy, more here, here and here. So when the molecule is vibrating, it is not uniformly all over the place. So when it is vibrating, it is not going to be like this. It will be like this, or next one is like this, next one is like this. So the probability is going to vary depending upon the vibration level, 0, 1, 2, 3 like that. Okay, so this tells you the distribution. P is equal to 0, it is here, and 1, it is here and here, 2 here, here, here. So as you see, as you go up the vibrational levels, the probability of the molecule is closer to the end than to the middle, and whereas when you come down, the molecule is closer to the middle. So this is somewhat like the atomic orbitals. When we say p orbital, we draw a picture like this. We think electrons are top and the bottom. It is not in the middle. And then when you say s orbital, it is all over the place. So something of that type. Okay, this is something that. Okay, so this is the one difference between everyday harmonic oscillator, that is two balls connected by a spring. If you think of the molecule like that, there is a difference between this picture and a real molecule, because always we think of a real molecule in terms of something we can see every day. A ball connected by a spring is what we can see. Two atoms connected by two electrons we cannot see. We can just have to imagine how it might be. So what we see is basically this line here. The real molecule, actually it looks like this. It is very close, but not exactly like this. If you notice, what happens is, in a real molecule, if you keep on putting more and more energy, it will vibrate, but at some point it will break. That is the chemical reactions. That is, you can see it here. So if you keep putting energy into this molecule, what will happen is it will vibrate between these two. And then if you put energy up to this much, it will vibrate between these two. So it will never break. It may stretch a long distance, come very close, but it will not break. But if you keep on increasing, let's say for example you start putting energy here, now it can go up to this, and then it will vibrate like so. What will happen is, if you have a lot of energy, the molecule is going to be vibrating between here and all the way down here. Now from here to here the distance is long. Now the electrons cannot hold the two atoms together. So next thing, if you put a little bit more, it will break. So this picture, which is true of the two balls connected by a spring, whereas for a molecule, this will at some stage it will break. That is what, how much energy it takes to break a bond is because of this. Because after a certain distance, it cannot bring the two atoms together. So that is the bond strength or the bond energy of any bonds. Okay, so this one you don't need. Okay, so this picture you should remember in your head. Okay, so the molecules can be represented by this kind of diagram. So when we represent an orbital, as I said, the orbitals we draw like this. When you want to represent a whole molecule, you put a picture like this, and in this picture these two centers represent the two atoms, and this one represents the vibrational levels. If you notice, there is, to go from here to here, it requires certain amount of energy. To go from here 1 to 2 requires certain amount. As you go up the ladder, the gap gets smaller and smaller, and eventually it becomes degenerate and then breaks. Okay, this is the normal picture we use every day in understanding molecules. Okay. All right. So let me see what else. Okay. Now I want to go back the whole thing what we talked today, and I want you to. I will ask some questions. Let's see whether you know what is the answer. Okay. So we talked about a whole bunch of things. Tell me, what are the basic laws of photochemistry? I talked about this morning. If you are going to do a photochemistry, what you should know? That is these two guys. I said something. This is called the Grothus Druper first law of photochemistry. Tell me what exactly you got. The people, some of you are here, I think most of the people who are here are there in the morning. Most of the people who are not here probably disappear. So what do you remember this? What is basic? There are two things which are very important for a chemical reaction or for anything to happen, whether you want to see a fluorescence or whether you want to do a chemical reactions. What are the two things that are important? Okay. You can discuss and then tell me. Between you can talk and then you can talk and then let me know what is the answer. It is pretty easy, straightforward. It is there in the notes. Okay, tell me what is the law number 1. You can read.
What's the question?
Huh?
That question.
The question is, what are the 2 important things that you should know before you do any experiments with light?
The light must be so
the light must be absorbed by the molecules. Okay, that is one. That means you should know the absorption spectrum of the compound. So you should know where the molecule is absorbing, so that you can use the appropriate light to activate the compound. That is important. What is the second important thing? I cannot also read, okay? This is pretty fuzzy for me, for you. So what is the second most important thing? Huh? Okay. So the second most important thing is, if you want to activate 100 molecules, you should have at least 100 photons. You cannot hope that the photons you can split and then give it to two different molecules. The one photon doesn't get into split into two or three smaller things. So either they all stay together as one. So if you, depending upon how many molecules you activate, so this is what is here. So this one, each photon of light is absorbed by only one molecule. So if you have more than one molecule in your flask, then you need more than one photon to activate that all the molecules. Okay. Right. So let's see what else. Okay. Tell me what is the light that we talk about? Is it a particle, or is it a wave, or is it both? Both. Okay. Okay. So we already we went through this one. We said the light it can be a wave or it can be a particle, depending upon with which it is interacting. If you want to define the light, what is the primary important factor? What is the thing that you have to know to tell whether this light is blue or green or red or something? How much energy it has? What is the thing that you will use? Okay, the answer is the one that I have highlighted there. So if you want to define a photon, if I want to do a reaction, or you want to irradiate a compound to see the fluorescence from a compound, then Dr. Leaping will tell you irradiate at this, use this light to activate your compound, and you will see the fluorescence. So what is the number or something that you will write down to activate a molecule? Wavelength. Okay, so wavelength defines how much energy a particular photon has. Okay, suppose you have a wavelength of 700 nanometers and then another one of 300 nanometers. Which one has got more energy? Okay. So you have the light of different wavelengths. So 700 and 300. The 300 one has more energy than the 700 one. 700 nanometers has lesser energy compared to 300. The energy of it is controlled by h mu. Mu is hc divided by lambda. H is fixed. H is Planck's constant. C is the speed of light divided by lambda. So division if it is 700, the number is going to be smaller. If it is 300, the number is going to be larger. It will have more energy. Does it make sense? Does it make sense? Okay, let's see. I will put this here. What happened? Okay. Can you tell me what is Born-Oppenheimer approximation? It is this guy. Okay. Tell me what is Born-Oppenheimer approximation? What is that?
Electron vibration faster than current with wave vibration.
I think you have to talk a little bit louder or I have to come closer. What is the answer?
The question is
What is Born? That is this Born-Oppenheimer approximation that we use, in calculating the energies of a molecule. That's it. In quantum chemistry, if you want to calculate the energy of a molecule, you make a major approximation. That is what we call as Born-Oppenheimer approximation. Okay, what is that approximation? Okay, when you think of a molecule has got at least three different things. It has got electrons moving around, and then it has got atoms always shaking around, and the spin which is exchanging. So if you want to define a molecule, at the same time you have to know the positions of the nuclei, positions of the electrons, and also the spin of the electrons. But it is not possible to know all three, because all the time everything is moving. So it is like everything is always moving around. So if it is moving around, there is no way you can calculate the energy of a molecule. To do that, to calculate, what we do is, it is not completely moving, it is staying like this. And then for that particular arrangement, you calculate the electronic configuration. But if you calculate this energy, it is not correct, because molecule is always doing something like this. But if it is always doing something like this, you cannot figure out where the electrons are. So what you do is, okay, it is staying like this, and you calculate that is what is called as the Born-Oppenheimer approximation. So you can make it as though the molecule is stationary, and you can calculate everything, and then you can slowly adjust your numbers, assuming it is moving. Okay, that is possible because the speed with which electron moves and the nuclei moves and the spin change, they are all at different time scales. So the fastest is the electrons. So when the electron is moving from one place to another place, the nuclei will not change, because electrons will go in 10 power minus 15 seconds. For this to move, it takes 10 power minus 12 seconds. So so if you assume the nuclei is stationary and then electron you move, so the assumption is correct. But when the thing is moving a little bit more, then you will have to readjust the original number. So that's how the calculations is done. If you say that everything is moving, so I don't know, I'm not going to calculate anything, that means you will not know anything. So the assumption is a very major assumption, but it is very useful assumption. It's called Born-Oppenheimer approximation. When you take a physical chemistry course or quantum chemistry chapter, you will come across this term. Okay? Okay, so let's see what else. So, as I already was mentioning, the time scales in chemistry are very important. Because the lifetime is how long a molecule lives in the excited state or how fast it reacts is controlled by the time change. For example, singlet and the triplet, they have different time scales. For example, if you take a molecule, put it in the singlet state where the two electrons have opposite spin, and then you put another molecule in the triplet states where the electrons have the same spin, they leave for different time. That means from there to come back down for singlet it will be faster. For the triplet to come back down it will be a little bit slow. Tell me which one will have a longer lifetime. Lifetime means how long it lives in some place. Okay, you take a thing and then throw it out, go to singlet. Another one you throw it, goes to the triplet. Which one will come back to you faster? Singlet or the triplet? Singlet. Okay, good. So singlet will come faster. That is, singlet will always have a shorter time scale, that is in the nanosecond, 10 power minus 9 minus 10 seconds, whereas the triplets will have 10 power minus 6 to minus 3 seconds. So tell me why singlet has a shorter time scale, triplet has a longer time scale. Why the triplet is longer, singlet is shorter. So we didn't talk about this before. Singlet means the two electrons have opposite spin. So if the electron wants to come back from the one orbital back to the other orbital, it doesn't have to change the spin. All it has to do is it is to go from that orbital back to the original orbital. If it is the triplet state, the two electrons have the same spin. So go back to the ground state, they have to have opposite spin. So to take the spin from one alpha, shifting it to beta, it takes some time. So usually what happens is the triplets will stay there longer because it has to find a way to change the spin, and it will take like 10 power minus 3 to minus 6 seconds. Whereas for singlet state, that's not a problem. It just comes back very quickly. Okay? Okay. When you say triplet, how many states are there in the triplet? So when you have triplet, are there 3 different configurations or only one configuration? How many, including spin? Or these 3 states when you write? Here we say S0, S1 and T1. We call them as T1. When you fire one line, T1, does it have 3 different lines or is it only one line? The answer is see, we could always, when you any book you see here, you will see a triplet, we similar to put like this. Is 0, we will put S1, and then we will put T1. So this one is assuming here we don't worry about the spin. Suppose we worry about the spin of the electrons. Singlet, how many states? Triplet, how many states? Triplet means 3. So when you have the triplet, the 2 electrons with the same spin, they will have 3 different spin states. That is alpha, alpha, beta, beta, and this one. So this triplet state, normally it has got 3 different states. So in fact it is actually looks like this. So the separations is very small. It will be like 0.5 kilocalories or even lesser than that. So we don't worry about it. So we just put as a single line. That single line, that when you say triplet, there are 3 states in that. But these 3 states, if they are almost degenerate, they will be equal reach. But in a magnetic field, you can separate this into 3 separate states. Okay. Suppose you have n to pi star and pi to pi star. Which one will have a larger singlet triplet gap? N to pi star, pi to pi star. Which one? The gap between the S1 and T1, which will have larger? Which one will have a larger gap? It is also this one went through different.
This one.
Huh?
This one. This one.
Yes, one? No. Singlet triplet gap, n to pi star or pi to pi star. Which of these two will have a larger gap? Between the S1 and the T1. Between the n to pi star. Another molecule with the S1 and T1, which is pi to pi star. Which of these two will have a larger gap?
T1. This one.
Huh?
T1. This one. So, larger.
No, I think the question is. So if you have n like a, if you have the electronic state, if you have the n to pi star electronic configuration, the energy difference between n pi star, which is singlet n to pi star, corresponding to triplet n to pi star, that is a singlet and triplet, and you have another molecule, pi to pi star singlet, pi to pi star triplet. So the gap between the singlet and the triplet, which of these two will be larger? Okay, so how many people think it is pi to pi star? One. Yeah, okay, I counted you. Anybody else? Which one? If you say pi to pi star, just raise your hand. So from there, at least I know.
Pi to pi star is larger than the
Huh?
triplet star.
What's that?
Pi to pi star is larger than the n to pi star. N to pi star.
Okay, so you, number two people agree, 3 people. So anybody else? Okay, so pi to pi star will have a larger gap. Because I explained this picture here before. Because if you remember, we said the gap is the larger the overlap, the larger the gap. So n and pi star, they are not overlapping that much. So the gap between the singlet and the triplet is smaller compared to the pi to pi star. Okay. All right. So now I think I want to start something new. It is slightly different from what we talked about. It is about absorption and emission. This is something which is very practical that you probably, some of you might be doing every day. Emission, fluorescence, phosphorescence, all that kind of stuff. Okay. So do you need a gap, some 5-10 minutes, or we just go? 5:50 we will stop, whatever happens. Okay, around 5:50. Now it is 4:30. You are all tired? Because almost 6 hours, we're talking the same things. So this is too much of photochemistry in one day. Huh? You want a gap? What is that? Okay. Okay. Gap? You want a gap or no? Yes? Okay, we'll take about 10 minutes, 5 or 4:45. We'll meet again. Okay. I know it's pretty long. I don't like these 6 hours lecture. I cannot stay here for too long. I also want to go back to Miami. So 4:45 we'll talk about it. Okay, all these cups are, you can throw all the cups and water bottles.